Good morning, Kansas City. Let's get ready to learn on KCPS Homeroom. I'm Justin Robinson, your homeroom instructor. Today is Math Monday. First, we'll have a math lesson for kindergarten through second grade, followed by a lesson for third through sixth, then middle school, and finally high school math, K through 2. Are you ready to learn? All right, let's go meet your teacher, Miss Barnes.
Good morning, everyone, and welcome to Math Mondays. I'm Miss Barnes, and together we are going to be learning about big math concepts for learners just like you. Today we're going to be talking about place value. Have you ever wondered why numbers are different sizes? For example here, 5, 50, and 500 are all different sizes. 5 has 1 digit, 50 has 2 digits, and 500 has 3 digits. Do these digits have different values? Do they mean different things? In order to talk about the answers to those questions, today we are going to read a book called Zero the Hero by Joan Holub. As we're reading this book, I'd like you to think about all of the ways we use zero in our lives. Sometimes that can be in math operations like addition or subtraction, and other times it could be used in situations where we're talking about numbers. As we're reading, please think about all the ways we use zero in our lives. Are you ready to get started? Zero the Hero by Joan Holub. Unlike most numbers, Zero believed himself to be a hero. He just needed a chance to prove it. Hey, who's that in that mask? From now on, call me Zero the Hero. Call you what? Now I've heard everything. But Zero's belief in himself didn't count for much when it came to fitting in. 1 little, 2 little, 3 little. Poor Zero, he's always getting left out of our games. In order to amount to anything, Zero had to stand in the shadow of others more glamorous than he was. Yes, it's true, I'm number 1, the number everyone wants to be. I take first place in every contest. I'm the number line leader. Oh, and when my pal Zero tags along, I become a 10. That's equal to 10 ones, of course, not 10 zeros. Occasionally, he was mistaken for various circular objects, seemingly at random. Some days it really got to him. Hey, aren't you a Fruit Loop? I love those. No, I'm Zero the Hero. Yeah, I don't think so. Are you a donut? No! When it came to addition, he was virtually invisible. Other numbers seemed to pass right through him, almost like magic. The same thing happened with subtraction. In their frustration, some numbers were unkind. Hey, diddly squat, any way I figure it, me take away nothing equals me, right? Am I right? Am I? Turns out, Zero stunk even more at division. So badly, in fact, that other numbers simply refused to be divided by him at all. Sorry, I can't be divided by nothing. What would be the point? Still, his belief in his wonderfulness persisted. Then one day, during multiplication, it was discovered that any number times 0 equals, you guessed it, 0. I apologize 100% for what I'm about to do to you. It's nothing personal. Here I am, another product of 0 times anything. Fearing extinction, the others ran from him. Who could blame them? Run for your lives! Good thing I've got 9 of them. Don't go near the times tables if 0's around, or you'll be toast. Burnt toast. As the others scurried away, Zero had a horrible realization. A real superhero wouldn't multiply his friends into nothingness. That's the kind of stuff only an evil villain would do. Could it be that he wasn't a hero at all? The thought gave Zero a hollow feeling inside. His confidence shaken, he tucked himself tight and rolled away, heading for infinity or oblivion, whichever came first. The counting numbers didn't even notice Zero was gone. As you can see, I've got these 5 apples. And I've got 2 bananas here. That is, until they encountered unexpected story problems. I've got 3 oranges. I think we know how much fruit we have altogether. Yes, but without Zero, I won't be able to solve this problem. He needs to stand here to help me make a 10. To take their minds off their problems, they tried playing a game of round off, but this proved impossible without Zero. This is no fun. Yeah, without Zero, we can't round down to 10, and we can't round up to 30. We feel so odd without Zero around. We miss Zero even more. No question, the counting numbers were missing their friend. In fact, they were so busy missing him, they didn't notice they were being surrounded. You know, I never told Zero, but I'm often mistaken for the letter S. Some confuse me with the letter Z, as in zero. Before the numbers knew it, they had been captured by Roman soldiers. In the name of the Emperor, we are taking you prisoner. Hey, aren't you the letter X? No, we are not letters, we are Roman numerals. We don't really like fighting. Instead, maybe we could teach you how to do math using ones, tens, and hundreds places. Roman numerals don't do math, we just count. One, 2, 3, 4, 5, 6, 7, 8, and 9 were tossed into the gladiator ring. The Roman soldiers were counting the minutes until they'd attack. It was a time of darkness and despair. From far away, Zero heard his pals call for help. This is a job for Zero the hero, he thought. Faster than a speeding donut, Zero zoomed to the rescue. Look up in the air, it's a flying bagel. Hey, my missing chariot wheel. A giant Cheerio, maybe? Release the numbers or else, Zero told the Romans. Or else what? The Romans replied. Or else I will unleash a force greater than you can imagine. The power of nothing. Go ahead, said the Romans. We're not afraid of nothing. Left no choice, Zero grabbed a nearby rock and proceeded to demonstrate his amazing power. Here goes nothing. 0 times rock equals 0. Ta-da! When the Roman numerals saw the rock disappear, they decided to disappear too. They ran away as fast as they could. He's going to do a number on us. Run for your life. Let's skedaddle. All hail Zero the hero, shouted the counting numbers. Thank you for saving us. With his friends around him once more, and the knowledge that he had fought evil and won, Zero no longer felt empty inside. Now that hollow nothingness inside him was filled with something, and that something was joy. The end. And that's the story of Zero the hero. Did you like it? I'd like to review the questions that we started with at the beginning of our read aloud. We were talking about ways in which Zero the hero help us every day in our lives and also in math. One of the ways that Zero taught us to use Zero during math is with addition. And we learned that 1 plus 0 equals 1. So when you add with 0, the number that you start with stays the same. We also learned that when you subtract with 0, the same thing happens. For example, 1 minus 0 still equals 1. We also learned that when 0 tried to divide, his friends told him they couldn't divide by 0. And when he tried to multiply, he multiplied his friends into nothing. But the most valuable lesson 0 taught us today in our book is that without him, you can't count past the number 9. We learned on one of the very first pages that without 0 next to a 1, we can't make a 10. It's this concept that we're going to talk about more next week as we dive in a little bit more with these numbers 5, 50, and 500 in order to talk about the difference in the value with numbers. I hope you join us next week. See you then.
Thank you, Ms. Barnes, and we will see you next week. Next up today, Ms. Dorsey with 3rd through 6th grade math. Everyone, let's get ready to learn.
Hi, my name is Erin Dorsey, and I am a math curriculum coordinator for the Kansas City Public School District. I'm so happy that you joined me this week. We're going to talk about problem solving. Let me tell you a little secret. I did not always like math. When I was a kid, math scared me. I thought it was too hard and I didn't think I could do it. And it was not my favorite subject in school until I realized that math is all over the place. So today we're going to read a story about math and problem solving and finding math in your everyday life. And hopefully by the end you'll realize that math really isn't all that bad. Today's story is called I'm Trying to Love Math by Bethany Barton. If you ask me, math is not very lovable. I know I'm not alone here either. 4 in 10 Americans hate math. That's like 40%. Did you just use math to explain how much you don't like it? A space alien? What do you know about math? Well, math is understood all over the earth, no matter what language you speak. That's pretty neat. 5 plus 2 equals 17. That's the same everywhere. Except you're not from Earth. Nope, but thankfully scientists sent math out to space. Scientists took examples of life on Earth, things like language, music, and math, and put them onto golden records. See all that math? Addition, fraction, multiplication, binary numbers? That's a ton of math. The golden records went on space probes they sent in deep into space for curious aliens like me to find. They sent you math? No wonder aliens don't come visit. They should have sent you cookies. What are cookies? I'll make you some. They're so much better than math. Let's see. I just need 2.5 cups of flour, 3/4 a cup of brown sugar, 1 cup of butter. Looks like I need 2 of these to equal a cup. Wait, baking is just a bunch of math, isn't it? Wow. In fact, this whole recipe is basically a math problem. Fractions, conversions, temperature, time, chocolate. But isn't that a good thing? Without those measurements and fractions, what would you end up with? A burnt pile of mush. I guess you have a point. Okay, you see this math problem here? 785 times 5. I'm gonna try to love it. Maybe if I stare at it and think about cookies, then I'll love it. 785 times 5. Nope, I'm already bored. What if I jazz it up with some extra numbers? Look at that. Think that's helping? And add some of these symbols. Whoops. You got a little carried away. This is way too much math. Can we shake the book and make some numbers fall out? Just hold it tight and give it a few good shakes. Whew. Thanks. Math is just so boring. It's not like you can dance to it. Actually, you can. Music has a lot of math in it. Look at the time signature, notes for each beat that tells you how many beats in a bar. Quarter note, or one beat, one bar. Look at all that math. In fact, it was a mathematician who discovered that different lengths of string produce different musical sounds. I didn't know that. Because of his math, you're able to make the guitars you have today. Well, thanks for ruining music for me. Now all I hear are numbers. I think you're missing the point. Math isn't all about numbers. Arithmetic, another word for math with numbers, is super helpful. But it's only one part of math. What do you think the other part of math could be? Think about that. Math is also about exploring, about finding new ways to get places and helping you find your way back. For centuries, sailors navigated using the stars, special measuring tools, and lots of math. Can you believe that? Sailors had to measure stars to get to where they're going? I bet they had to use a lot of math. Modern explorers calculate how much force and fuel is needed to get a rocket past your atmosphere and out into space. Take that, gravity. Speaking of exploring, you've barely checked out Earth. We have lots of beautiful things to see. Look at all these beautiful things to see. Symmetry, where two or more parts match each other. Ooh, that looks like some math. Math is here in your nature too. Math is about finding shapes and patterns. Oh, no, you don't. You're making it all about math again. But it's my turn to teach you something. Introducing Earth's greatest invention, pizza. Think there's math in pizza? Let's find out. That does look interesting. How big is that thing? Oh, that's easy. It's, wait, how do you measure this thing? I know, and the answer is as easy as pi. Pi represents a number. It's a super long number, so you usually shorten it to 3.14. This is pi, not that pi. It's a sort of cheat code to figure out the size of a circle. Pi is also what's called an irrational number, which means it goes on forever and never repeats, like this. Well, that was unexpected. I never thought I'd say this, but this is too much pie for me. That's an easy fix. Let's just grab the book and shake all this pie off the page. Whew, that's better. I'll admit, some of this math stuff is pretty cool. I'm okay. But math can still be pretty frustrating, like how there's only one right answer. That's true. But it also is what makes math so helpful. Math gives us a set of rules that everyone can agree on. So we know how far to travel to get places, how fast we're moving on our way, and how much things cost when we get there. I like that about math too. I like that there's only one right answer. Well, I'm ready to test that out. You know, math is a part of so many things I already love. I guess I don't need to try to love it at all. It turns out I already do. Thanks for your help. Where do you say you're from anyway? Great, you love math. My work here is done. Time to head home. Planet homework. Yikes. I really like this book because it talks all about the math that you deal with every single day, but it's also kind of funny. And what it makes me realize is that you don't have to be scared of math. All you need to do is give it a try. Next week, we're going to take a look at how to be a mathematician and how to look at situations and find solutions. And while there's only one right answer, there are so many ways to go about solving it. And that's what we're going to talk about. I can't wait to see you next week. Thanks for joining me today.
Thank you, Miss Dorsey. Can't wait to see you next week as well. Now it's time for middle school math. Okay, 7th and 8th graders, let's get ready to learn from Mr. Ravindran.
Hey everybody, welcome back. This is lesson 5 for 8th grade math. I'm Mr. Ravindran. Let's begin. Today's learning target, I can solve two-step equations in one variable using inverse operations and determine the number of solutions an equation has. As usual, go ahead and pause the video at this time so you can copy down the learning target. All right, excellent. Now that you've copied down the learning target, let's resume. So, when we're solving an algebraic equation, we're going to be using what's called inverse operations to isolate a variable. Inverse operations, as we'll explore on the next few slides, are the opposite of GEMS or PEMDAS. Let me explain a little further. They're the opposite of the order of operations. Inverse means opposite. So we're going to be using inverse operations to isolate a variable. So we're actually going to, instead of starting with parentheses, we're going to start with subtraction and addition. First, perform the opposite of add, subtract on both sides of the equal sign. Second, we're going to perform the opposite of multiply and divide on both sides of the equal sign. Go ahead and pause the video to copy down these notes. Excellent. Now that you've copied down these notes, let's move on. Here's example number 1. It says solve using inverse operations. So we're going to go to our document camera. Excellent. Here it is. And we're going to write down example 1. So this is EX1. Well, example 1, let me just go back and grab it, is 5x plus 10 is equal to 25. So our task is to isolate x. So let's take a little note here. Let's write the word isolate. Isolate means get it by itself. So we need to get x by itself. We're going to be using inverse operations. Inverse ops. So we're starting with add, subtract. These little notes that I'm writing off to the side, I strongly encourage you to write the same. So we're going to be starting with add, subtract. One thing I recommend is that you put a line through the middle of the equal sign. This line is your IO line, your inverse operations line. We need to start with plus and minus, add and subtract. Well, the 5 is multiplying, but what's the 10 doing? The 10 is adding. So we're going to be doing the inverse of adding, which is subtracting on both sides of the equal sign, on both sides of the IO line. So I see a plus 10. How do I get rid of plus 10? I do minus 10 and minus 10 on both sides. This is why we're performing inverse operations. Because by subtracting 10 on both sides, we can cancel 10 minus 10 out. That is an additive inverse property. The 5x drops down because we didn't touch it yet. The equal sign never moves. And now we can simplify on the right-hand side. 25 minus 10 is, of course, 15. So we now have 5 times x, which is 5 times some number equals 15. Well, what task do we need to do now? Now we need to get rid of the times 5. We're going to do inverse ops, IO, again. And this time, we're going to do the opposite of multiply, which means we need to divide. Exactly correct. We need to divide. So if we see 5 times x, how do we get rid of 5 times x to get x by itself? We show division. And now that you guys are getting into 8th grade and 9th grade, or into higher levels of math, we're going to show division like a fraction. So this is simply division over here. So 5 divided by 5, and also on the other side, on both sides of the equal sign. Now we cancel out. 5 divided by 5 is 1. So it disappears. It's just 1 times x, which is to say x. We've now isolated x. X equals 15 divided by 5, 3. X equals 3. That's the answer. That's the solution. So we went from a 2-step equation to a solution. 2 steps. First, get rid of the plus 10 with minus 10 on both sides. Then get rid of the times 5 with divide by 5 on both sides. We get one solution. Well, let's talk about that solution. We're going to switch back to the slides now. Let's go ahead and take a look at this. It says 5x plus 10 equals 25. When we solved it, we got x equals 3. So what this means is any place we see the letter x, we should actually put a 3. And then we can say if it's true or false. So right here, it's actually going to become 5 times 3 plus 10 equals 25. There's no more variables. We got rid of the variable x, and now it's time to see if we were right. Well, were we? Let's solve. First, using order of operations, we need to do 5 times 3. That's 15. 15 plus 10 equals 25. Well, is that a true statement? Does 15 plus 10 equal 25? Of course it does. We know this. You know this. 15 plus 10, we end up with 25 equals 25. Is that a true statement? Yes, this is a true statement. So this is very important. So we're going to put this down and highlight it. There's only one solution because only x equals 3 will make this equation a true statement. Only x equals 3 yields 25 equals 25. So at this time, pause the video. Make sure you have copied down what I'm just highlighting right now, the solution. And if you need to, rewind the video to make sure you have this work shown. In fact, let me put them side by side so you can see them both at the same time. Go ahead and pause the video to copy down the highlighted section over here, as well as the solution over here. All right, great. Now that you've paused the video, or rather unpaused the video, you finished copying this, and you finished copying what's on the screen over here, you are ready to move on to example number 2. Well, example number 2 is similar. It says solve using inverse operations. So I'm going to maximize the screen. First, I'll write it down. Let me just carve out some space in my notebook here, my math notebook. This is going to be example 2, EX2, and we'll write it down. Negative 4x plus 2 equals 26. Now I will maximize the screen. So we're going to solve this equation. Similarly, per the other problem, I like to personally start with my IO line, my inverse operations line. This is my IO line. Whenever I go over this line, I do the opposite. I'm going to start with IO for plus and minus, the opposite of plus and minus. So I'm looking for a plus sign so that I can do the opposite, or I'm looking for the minus sign so I can do the opposite. Let's look at the 4. 4x, negative 4x. This is multiplication. So that is not addition. That's multiplying. But the plus 2 can be gotten rid of. How do we get rid of it? Well, we do minus 2 on both sides. This is additive inverse. Plus 2 minus 2 yields a 0. It cancels out. We can drop this down. Negative 4x equals, notice the equal sign didn't move. The 4x we didn't change, so it just falls down. And 26 minus 2, we can simplify this to make 24. Next up is IO for multiply and divide. Well, is there any multiplication going on? Yes. The negative 4 was multiplying the x. This negative 4 is multiplying the x. So how do we get rid of it? We use inverse operations, opposite operations. We're doing the opposite of multiplication, so we divide. Again, we're going to be using it. We're going to show our work like a fraction. this cancels out because negative 4 divided by negative 4 equals 1. So that just disappears because 1 times x is x. So now we have x by itself, and all we need to do is divide over here. 24 divided by negative 4. Well, a positive divided by a negative is a negative. And now it's simply, how many times does 4 go into 24? 4 goes into 24. Let's think about that. 4 times 5 is 20. 4 times 6, 24. Negative 6. It has to be negative because a positive 24 divided by a negative 4 makes a negative 6. So we now get x equals negative 6. And that is one solution. Only one number will work here. Only one number fits right here. Let's go back to our slides and make sure we have that done. But before we do that, pause the video. Make sure you have example 2 copied down. Great. Now that you've unpaused the video, let's move on to check our solution. Well, here's what we had. We solved the equation and we got x equals negative 6. Let's see if that's true. Again, any place we see the letter x, the variable x, we're going to plug in. We're going to use algebraic substitution and we're going to replace it. So now I'm just going to copy this really quickly. I'm just going to copy that. And I'm going to, instead of x, I'm going to put parentheses negative 6. Now we'll solve. The first step is to multiply these two terms. A negative times a negative is a positive. So negative 4 times negative 6 is 24. So these two terms become 24. 24 plus 2. Does that equal 26? Yes, it does. So we end up with 26 equals 26. That is a true statement. That is a true statement. So because it's a true statement, only x equals negative 6 will make the equation true. You have to have a negative 6. No other number will work right there. Great. Pause the video, copy that down. Excellent. Now that you've copied that down, I want you to pause the video and try to solve this equation by yourself. 7x plus 3 equals 17. Also answer, how many solutions does the equation have? Excellent. Now that you've solved it by pausing and giving yourself time to work it, let's see if you got it right. We're going to go back to our document camera and let's check our work. The equation was 7x plus 3. Oh, whoops, can't see that. 7x plus 3 is equal to 17. Once again, we're going to start with the line down the middle and we're going to get rid of plus minus. Well, here we see a plus 3, so we'll do minus 3 on both sides. Cancel. 7x drops down, equals 17 minus 3 is 14. And now one final step. Divide by 7, divide by 7. Now we've isolated x, and 14 divided by 7, we get x equals 2. One solution. Let's see if that works over here. If we plug in 7 times 2 plus 3 equals 17. Let's see if it's true. 7 times 3, 14 plus 3 equals 17. That's true. We get 17 equals 17, which is true. Because it's true, there's only one solution. Only one solution. The only solution is x equals 2. Only x equals 2 will work. Make sure you have this copied down and make sure you have the notes over here copied down, everything on the slide. Now let's move on. Pause the video if you need to make sure you have this all sorted out. Now we're going to move on. Great. How many solutions can an equation have? Most equations have one solution. This is the second part of our learning target. And for some of us, this may be new material. How many solutions can an equation have? Let's consider this equation. X plus 3 equals 5. What number plus 3 equals 5? Do you know what it is? Well, let's use inverse operations to solve. Minus 3 minus 3. We get x equals 2. These two 3's cancel out. So really, I should have, let's say, insert. Let me put a little line there. cross these out. This is additive inverse. I'm going to cross those out with a nice red line. Make it pretty bold too, so it really is gone. So those two cross out. When you do that plus 3, they cross out. Maybe a little less bold, like that. Anyway, where were we? So we did the opposite of plus 3, minus 3 on both sides. We get x equals 2. Only x equals 2 will make this a true statement. The only number that when you add 3 to 2, it equals 5. That's the true statement, only 2. So this one has one solution. But some equations have no solutions. An equation has no solutions if no value of x will make a true statement. No value of x makes the equation a true statement. What does that mean? Let's take a look at this. X plus 2 equals x. Imagine that x was anything you could possibly think of. X is a basketball. How can a basketball plus 2 equal a basketball? Maybe it's not a basketball. Maybe it's a Ferrari. Ferrari plus 2, how could that equal a Ferrari? Maybe that's confusing to you. Let's use a number. Let's take the number 10, a nice round number. Let's say that maybe x was equal to 10. So 10 plus 2 equals 10. Is that a true statement? No. We end up with 12 equals 10. This is false. So it's not a solution. Let's try another number. Let's try, 3. 3 plus 2 equals 3. Is that true? No, that's also false because this would equal 5. No number will make this true. No number when you add 2 will equal itself its original value. This is no solution. So all you would write here is no solution. No answer makes this true. No solutions exist. It is false. One look for here is that it is unbalanced. We have x and x on both sides, but plus 2 is only on one side. So it is not a true solution. It'll never work. Let's move on. Finally, some equations will have infinite solutions. Oh, my mistake. Let's go back just a second. Pause the video here to copy all this down. Make sure you have this in your notes. Please pause the video and copy that down into your notes. Great, now that you've unpaused the video and you're ready to move on, let's talk about infinite solutions. Some equations will have infinite solutions. What does that mean? An equation will have infinite solutions of any value of x will make a true statement. No matter what x is, it'll be true. Here we see x plus 5 is equal to x plus 3 plus 2. Well, is there anything we can do on the right-hand side of the equation that we can combine? Sure. X plus 3 plus 2 can be combined. So we have x plus 5 equals, 3 plus 2 can be added together. Those are like terms. That's x plus 5. What do you notice about both sides? Really importantly, they're the exact same on both sides. No matter what you put here for x, it will be true. So let's take the number 10. Let's say x was 10. If x equals 10, what are we left with? We're left with 10 plus 5 is equal to 10 plus 5. Is that true? Yes, that's true. Let's try another one. Instead of 10, let's try 3. 3 plus 5 equals 3 plus 5. Is that true? Yes, that's true. So both x equals 10 and x equals 3 work. Well, any number will work. That's why we say it has infinite solutions. No matter what x equals, the equation will be true because the equation is the exact same on both sides. That's really important. So recapping. One solution. Only one number works. 2 plus 3 equals 5. Only one number will work. No solution. It's unbalanced. X plus 2 could not possibly be equal to x. No number, if you add 2 to it, will be equal to that original quantity. It's unbalanced. No number will make a true statement. Finally, infinite solutions. Any number will work. An infinite solution means that any value of x will make it true. Because x plus 5 is equal to x plus 5. Yes, we had to add the 3 plus the 2, but those are like terms. But look, when we did 10, we got 15 equals 15. When we did 3, we got 8 equals 8. Pick any number you want and it'll work. Maybe you don't even choose a number. Maybe you choose a thing. I don't know. How about a Ferrari? Or let's say, I don't know, not a Ferrari. We already did a Ferrari. So let's say a piece of candy. Is a piece of candy plus 5 equal to a piece of candy plus 3 plus 2? Yes, because that's a piece of candy plus 5 equals a piece of candy plus 5. Anything works here. It's true because it's balanced. All right, now that you have copied down all the notes, it's time for you to try task 5, which your teacher will have assigned to you on Google Classroom. Thanks for watching. Hope you have a great day. See you next time.
Thank you, Mr. Rabindran. Last class for Math Monday is for high schoolers. We have an exciting lesson from Miss Fender. Let's get ready to learn.
Good morning and welcome to Monday Math. And today we're going to talk about surface area and some geometry, but I want to put it in context for you. We're going to be having you do a simulation. You're going to be an interior design intern. And our company, we're going to call it KCPS Interior Design. And your job is going to be taking a potential client, creating a portfolio for them, and seeing if that meets their needs, and then later on maybe going back and adjusting if you're over budget, they don't like the curtains or something like that. But the first thing we need to do in our project is we need to figure out surface area of the floor and then surface area of the walls, because we don't want to overspend on the floor covering. If you go into Lowe's, Home Depot, any of your supply stores, they're going to ask you a couple of questions. Number one is, what is the surface area? How much of that material do you need? So let's talk about that today. Before we get started, if you haven't gotten your paper, pencil, maybe a calculator if you need that, take a moment, very quickly, get that underway. And let's get started. Now, when we talk about surface area, we're talking about a shape. And most of the time in architecture, we're talking about squares and rectangles. And sometimes my squares look like rectangles and vice versa. So if you bear with me, we can tell that by the number of rows and the number of columns we have. Now, most rooms are going to be a square. They're either going to be 10 by 10, 11 by 11, 12 by 12. Your living rooms and things like that are going to be rectangles, like 11 by 14 or 10 by 15. So let's talk about how many squares we have. Now, when we do this, we're going to talk about the number of rows. And this is going to be our length. And the number of columns is going to be our width. And there's a formula for that. And that's going to be length times width. Now, in the lower grades, your teachers or whoever's talking about surface area with you are going to say, how many squares are they? And they're going to count each and every square. As you get older, that's really not going to be efficient. You're going to say, really? I know how many squares. I can count faster than you can. So what we're going to do is we're going to use area equals length times width to help us out to speed this process along. So if you take a look, we have 1, 2, 3, 4 rows, and we have 5 columns. And we can come over here and we can say area equals 5 times 4, or you can say area equals 4 times 5. Really doesn't matter if you get your length and width mixed up, because shapes rotate. So when we multiply that, we know 4 times 5 is 20. And so our area is 20 square units. Now, if you walk into a building supply store, they're going to say, okay, is that feet? Is that yards? For right now, we don't care. We're just going to say feet. So this could be 20 square feet. So we need 20 square feet of material. Or if it's a bigger project, we could say meters, whatever. Okay? So let's do another one. Let's this time do a square. Okay? So our square is going to have the same number of rows and the same number of columns. Same process. What is your length? What is your width? Okay. And we can use the same formula, 3 times 3. We know that is going to be 9. Okay. But as older kids figure out, 3 times 3 can be written much more quickly, or more quickly, by saying 3 squared. And 3 squared, using our powers, is the same thing as 9. So our surface area of this particular square is 9 square units. That's a quick and easy way to do our surface area. Now, if we think about an actual room, I'm thinking about my office at home. And my office at home is a square. And I really want you guys to do this at home. I'll give you a few moments so you can do your calculations. I'm not going to draw the boxes this way. I'm just going to give you the dimensions. So my office at home is 12 feet by 12 feet. Now you have 2 ways of doing this. Because it's a square, we can do area equals, we're going to say side square. Remember, side is the same thing as a length or a width. Or we can say length times width. Either way is going to get you the final product. Depends on which way you think is faster. So when we do this, our dimensions are 12 by 12. Right now you should be thinking, okay, 12 times 12, what is that? 144. So the amount of material that I need to do for this is 144, and I wrote units. I already told you the units was feet. So the amount of material I need for this is 144 square feet. Okay, so here is our square. What if your room is a rectangle? So let's talk about that real fast. I'll use my dining room. I'm actually redoing it. It's a mess. If your parents are out there redoing something, don't tell them, okay? So we have our rectangle, and the dimensions of my dining room are 9 feet by 10 feet. Not overly big, but enough to get a table, some people in there. So when we talk about surface area, again, remember we're talking about rows and we're talking about columns. How many squares can we fit in here? These squares are going to be 1 foot by 1 foot. So we're going to say length times width. Our length is going to be 9. Our width is going to be 10. So our area is going to be 9 by 10. Now, some students think that length always has to be longer than width. Sometimes your object rotates. It's okay to have the width longer than the length. It's kind of like one of those things teachers do to say, okay, we need to turn your picture a certain way, but it really doesn't matter. So then our area is going to be 90 square feet. Now, on a drawing, you can say, okay, I've got my 90 square feet, but do you really understand what that means? So if you think about a ruler is about this big, and you place a ruler, and you place 2 rulers, and you kind of connect the dots. That's how big a square foot is, and that's what your people at your home supply store is going to be looking for. That's what you're going to be looking for on your floor or your windows or your wall, whatever it happens to be for surface area, for feet. So this would be 1 foot, 1 foot, so the area is 1 square foot. We talked about the floor. Now let's talk about the walls. And there's something special about all walls. They have windows. And windows, you don't count in your surface area because you don't want to, if you're doing wallpaper, you're gonna buy too much. If you're painting, that might be an extra gallon. And last time I went to buy a gallon of paint, it's really expensive. So we don't want to spend any more money than what we have to. So we're going to use my dimensions of my house at home. And so the room I'm thinking about is my living room. And my living room has 10-foot walls. So that's going to be our width of our rectangle. And the length of my room is 14 feet. So if you think about this gigantic wall, 10 foot high to the ceiling, 14 feet long, and it has a gigantic bay window. I love it because I have 2 kids. I can watch what they're doing outside, catch them before they do anything incorrectly. The window has its own dimensions. It's going to be 4 foot by 6 foot. Now, when we talk about taking that window out of the wall, we're only going to be painting this area right here. I do not want to buy paint for the window. That's going to cost me money. I don't want to spend it because I have money to spend on other things. So we're going to take the area of my wall. I'm going to take the area of my window. I'm going to subtract the area of my window to give me the area for the paint. So when I go buy my paint, I can say, hey, I need this much square feet, and he can sell me a quart versus a gallon, okay? So remember, area of a rectangle is length times width. And our length is 14. Our width is 10. It's okay if you reverse because you're still multiplying. Community property of multiplication says it doesn't matter which order, it still comes out to be the same thing. So that's going to be 140. And I'll go ahead and put labels on it, square feet. That's my wall. Now, when you're doing math, it's always good to label because you never know when you're going to have that time you have to walk away and then come back and go, oh my goodness, what did I do? I don't want to start over again. So my window is going to be 4 by 6. Now, I always write my formula first. Kids always say, why do you do that? It's a bad habit, but it's a great habit if you are in a job that requires you to show math, because they can now see what you're actually using as your equation or your formula, because you always want somebody to go back and check you. It's never a bad thing to say, hey, mom, dad, brother, sister, someone, can you check my math real quick? I want to make sure it's accurate. I want to get all my points. So then my length is going to be 6. My width is going to be 4. So that means my area is 24 square feet. Now remember, my window is not going to be painted, so I need to subtract that. So I'm going to say 140 minus 24 is 136 square feet. This is how much paint or wall covering, I'm going to choose paint because paint's my thing right now, 124 square feet, 136 square feet of paint. Now, it just happens for me to know that's 1 gallon of paint, okay? So I'm only going to need that amount of square footage, 1 gallon paint, that's all I need. What if I have the same dimensions, but I have 2 windows instead of a bay window? Hope that looks like a rectangle. So this is going to be my 10 feet. This is going to be my 14 feet. We've already done that math problem. So I'm going to write that off to the side. So I know that's 144 square feet. Okay? Now, I have two windows. They're going to be square. I hope it looks like a square, okay? And they're going to be the same size. They're going to be 2 feet by 2 feet. And I know 2 feet by 2 feet by using the same formula. Is 4 square feet. I have two windows, so I'm just going to multiply that. So this is my wall. This is my windows. I have two at 4 square feet each. So my total for my windows are 8 square feet. And my brain is getting ahead of my pen. Now, remember, I do not want to paint or whatever I'm doing to this, so I'm going to subtract. So I have my 140 minus the 8, and it's bleeding into my dimensions. Okay, so it's a good idea to box it in. So it's 132 square feet for my surface area that I need for this particular wall. And I just happen to know that's 1 gallon of paint, okay? So that is how you figure surface area of a wall. Previously, we learned surface area of a floor. Now you should be good to go to whenever you go to your home supply store. And they say, how much do you need? You can draw them a picture, fill out the dimensions, and you can figure it out for yourself. I hope you learned a lot about surface area today so that you can help your parents or even you if you want to redecorate your own room. That's all for today. Next week, we'll continue on with our simulation of being an interior designer. Have a great week and see you then.
Thank you, Ms. Fender, and thank all of you for joining us for Math Monday. Thank you to all of our wonderful instructors today. Tomorrow is English Language Arts Tuesday. We will see you all then. And students, remember, keep learning throughout the day.